position of a point with respect to the hyperbola. Now, as in the previous case, we have discussed about the position of a point leading to three cases. One is the point lying inside the ellipse or parabola, and the point P lying on the ellipse and P lying outside the ellipse. Similarly, we define for hyperbola and its respective position of a point divided into three cases. One, case 2, and case 3, where my hyperbola taken in case 1 case 2 and case 3. So in each of the three cases, as we have taken as case 1, case 2 and case 3, my case 1 has the point P which is outside the hyperbola, and case 2 where P is inside the hyperbola, and case 2 is P is inside, and case 3 P is on the hyperbola. This. So with each of the cases, we identify that here P is outside, P is inside, and P is on the hyperbola. Mathematically, we have a formula where if I take the equation of hyperbola in standard form as x squared by a squared minus y squared by b squared minus 1 equal to 0, then we have three cases coming out of this point connected with standard equation of hyperbola. So in case 1, we say that P is outside if S11 is greater than 0. This is case 1 of the point. Now P is inside, then we say S11 is less than 0 out here. Now in case 3, P is on the hyperbola, so I have S11 equals 0 is what we get for the case 3. So each of the cases, case 1, when P is outside the hyperbola, S11 is greater than 0. Case 2, if P is inside the hyperbola, S11 is less than 0. Case 3, if P is on the hyperbola, S11 is equal to 0, is how we understand the position of a point with respect to the hyperbola, divided into three cases, case 1, case 2, and case 3. Lateral recta, or the lattice rectum, which is the plural form, read as lateral recta. Let's see what is the lattice rectum. Now in case of ellipse or parabola, we have defined the lattice rectum as a line or the chord which passes through focus and which is perpendicular to the major axis. Similar is the case where this is the line or the chord which passes through focus and perpendicular to the transverse axis. Let's see how the lattice rectum looks for the standard form of hyperbola. So when I draw the hyperbola, I have the hyperbola with center as origin, and of course its x-intercepts are AA dash, and this is B and B dash, with B is A root E square minus 1 is the distance what we get out here. The distance CB, which is origin, is A times root of E square minus A, where A is CA given out here. So this is A and this is B, and I have the equation of hyperbola is x squared minus a squared by minus y squared minus b squared equal to 1 with A greater than B. Now for here, we know that the foci are S and S dash clearly out here. So a lattice rectum is a chord which passes through focus and perpendicular to the transverse axis, that is x-axis out here. So if I drop a perpendicular and a chord to the hyperbola, then this is called the lattice rectum passing through S. Similarly, if I drop a perpendicular from S dash, I get M dash, which are called the lattice rectum. So L dash and M dash are called latera recta for the given hyperbola. So with these two latera recta, let's see what are the endpoints of the latera recta. Now as we know that the coordinates of S are AE, 0, then this would be AE, B squared by A. Coordinates of L is AE, B squared by A, and the coordinates of L dash are AE, minus B squared by A. Is how we get the extremities of the lattice rectum, as L is this and L dash is this. Similarly, let's find the extremities M and M dash for the other lattice rectum passing through S dash. Now clearly this would be minus AE, B squared by A, or minus AE, minus B squared by A. So there are totally 4 extremities, L, L dash, M dash, which are the extremities of the lattice rectums LL dash and MM dash respectively. And clearly I find that this length is the y coordinate, that is B squared by A, and this length is also the y coordinate, which is B squared by A, and therefore length of lattice rectum, where this is equal to this, has is how we get. So length of lattice rectum is B squared by A plus B squared by A, which is 2B squared by A. That is, length of lattice rectum is 2B squared by A units, and both the lattice rectums are equal, that is LL dash is equal to M dash. So latera recta and their extremities and their length is what we have discussed in the session for the hyperbola in standard form with A greater than B. Equation of tangent. Let's see the equation of tangent for an hyperbola. That is, if I have an hyperbola in standard form, then for this hyperbola whose equation is given in standard form as x squared by a squared minus y squared by b squared minus 1 equal to 0 for a greater than b, let me take tangent t at p x1 y1, that is, this line touches the hyperbola at p x1 y1, and therefore we get the point of contact as p. Now I want to find the equation of tangent t at p x1 y1. which is given as equation of tangent t at px1 y1 with respect to the hyperbola s equal to 0 is given by s1 equals 0. So the equation of tangent is given by s1 equal to 0, which when simplified gives x1 by a square minus y1 by b square equals 1 is the equation of tangent at px1 y1 with respect to the standard hyperbola s equal to 0, and P is called the point of contact. This P is called point of contact, is how we understand the tangent at the point of contact P x1 y1. Now let's see equation of tangent in parametric form. Now we know that the parametric equations of the ellipse are x equal to a secant theta and y equal to b tan theta. Now let's see the equation of tangent in parametric form. Now for this hyperbola which has parametric equations as x equals a secant theta and y equals b tan theta for 0 less than or equal to this less than 2 pi, let me find the equation of tangent in parametric form. Suppose so here, this is the point of contact where the tangent exists. Now since I want equation of tangent in parametric form, I take the parametric point P of theta, that is a secant theta, and b tan theta. Theta is the angle made by the tangent with x-axis out here. So therefore, in order to find equation of tangent at P of theta, we are going to find using the formula. Equation of tangent T at P of theta with respect to the hyperbola and parametric equations is given by the equation x by a secant theta minus y by b tan theta equal to 1 is the formula for equation of tangent with respect to s equal to 0 is x by a secant theta minus y by b tan theta equals 1. Equation of normal. As we have seen the equation of tangent for the hyperbola, let's see the equation of normal at P x1 y1. For the hyperbola S, which is given by x square by a square minus y square by b square minus 1 equal to 0 with a greater than b. Now in this case, I have the normal which is perpendicular to the tangent and passing through the point of contact. So this is the normal which is perpendicular to the tangent. So n is the normal. So equation of normal at Px1 y1 with respect to the hyperbola s equal to 0 is given by the formula a square x by x1 minus b square y by y1 equals a square plus b square. So equation of normal is given by a square x by x1 minus b square y by y1 equals a square plus b square out here, where the normal is perpendicular to the tangent, is how we get out here the normal with its equation for the standard equation of hyperbola out there. Now let us take the special case of the vertices a and a dash. So what is the equation of normal at the vertices? So for example, I draw a tangent out here, then x-axis is perpendicular to the tangent. So if this is the tangent, this will be the normal because this is perpendicular to this and passing through A. Now for the point of contact here, similarly, if I draw the tangent, then this will be the normal out for this tangent. Therefore, the exceptional case is that at a0 and a dash minus a0 equation of normal is x-axis, or the equation of x-axis being y equals 0. So equation of normal is x-axis or y equals 0 is how we understand the normal connected with the vertices as the special case. Similarly, let's see the equation of normal in parametric form. That is, if I take the hyperbola in standard form, and let me take the tangent at the point of contact P of A secant theta and B tan theta, which are the parametric coordinates, then at this point of contact we know that there is a normal which is perpendicular which is called the normal. Now, in order to find equation of this normal in parametric form, where theta is this in the anti-clockwise direction, then equation of normal in parametric form is given by equation of normal n at the parametric point P of theta with respect to the hyperbola s equal to 0 is given by ax by secant theta plus by by tan theta equals a square plus b square, and of course with the limitation that theta is not equal to 0 and pi. because if theta is equal to 0, we get x-axis, that is theta equal to 0 implies normal is x-axis, and theta equal to pi implies also normal is x-axis. So excluding these two exceptional cases of x-axis being a normal at A and A dash, we get the equation of normal given by this for all theta lying between 0 and t pi, except at 0 and pi where the normal is x-axis. Condition for tangency. What is the condition for a line to be a tangent to the hyperbola? Or what is the condition for a line to touch the hyperbola is what we're going to discuss in this session. So the condition for tangency is related with the standard form of hyperbola, which I take out here with x and y, and then this, and then suppose I have a line which is a tangent to the hyperbola given in standard form, or as x squared by a squared minus y squared by b squared minus 1 equal to 0 with a greater than b, then the condition for this line to be a tangent is, for this line y equal to mx plus c to be a tangent to the hyperbola, this is c square is a square m square minus b square. So we have the condition for tangency for the line y is equal to mx plus c to touch the hyperbola. This is c square equals a square m square minus b square. Now let's find equation of tangent using condition for tangency. Now as we know that the condition for tangency is c square equals a square m square minus b square is the condition for the line y is equal to mx plus c to be tangent. We have c with plus or minus root of a square m square minus b square. That is, there are two values for which I correspond. So one is with c equals root of a square m square minus b square, and other with minus root a square m square minus b square. So how do we get these two lines is the biggest question. Therefore, c has two values, one given by plus and one given by minus, and therefore c equals plus or minus root of a square m square minus b square gives rise to two cases of the lines. So one of the line is y equals mx plus root a square m square minus b square, and the other is given by y equals mx minus root a square m square minus b square, one with plus and one with minus. So every pair of tangents are given with equal slopes. Therefore, the condition for tangency leads to equations of two tangents, one given by y equals mx plus root a square m square minus b square, and there's another tangent which is parallel, and then that is given by to this, and that is given by the equation y equals mx minus root a square m square minus b square are the two pairs of tangents, parallel tangents, which we have given by two equations. T1 parallel to T2, and equations of tangents are given by y equal to mx plus or minus root of a square m square minus b square is how we identify the tangent of the hyperbola. Also, as we see that there's something inside the root, therefore continued out here, I get for a square m square minus b square greater than 0, or m square greater than b square by a square, there exists always two tangents which are parallel to each other. There always exists two tangents which are parallel to each other in pair. In pairs is how we understand the property where this tangent is parallel to this given by plus or minus, and is how we understand the pairs of tangents. There exists at least one pair parallel to each other and given by the condition for tangency.